In the previous lecture we have discussed the balance equations approach, in which we converted the Boltzmann transport equation into a set of balance equations for carrier concentration, for current density, for kinetic energy density, and so on. This we achieved by multiplying the Boltzmann transport equation with a function of momentum p and then integrating the result over various allowed states. We worked out what will be the various terms of these balance equations. Now in this lecture we would like to develop the balance equations further, see how the equations can be used to model velocity saturation, velocity overshoot, velocity field curve, and so on. The balance equations are the ones which are most often used for device modeling, and one rarely uses the Boltzmann transport equation itself. Now let us see the arrangement of the balance equations. To solve for the carrier concentration n, we need the information about the carrier current density Jn. This is obtained from the momentum balance equation. Okay. So here this equation expresses the current density Jn. However, what you find is that you have got a new variable, namely the kinetic energy density. So you need to know Wn if you want to solve for Jn. Now where do you get the Wn from? You get Wn from the energy balance equation. But then this seems to be going on and on, because now you have introduced the kinetic energy flux Fw. So how do we get Fw? Well, the way out would be to write another equation. Now there seems to be a problem, that you seem to have infinite number of balance equations. So the equation for carrier concentration introduces the carrier flux Jn. The equation for Jn introduces the kinetic energy Wn. The equation for kinetic energy introduces the kinetic energy flux Fw, and it goes on and on. So how do we deal with this situation? The situation is carrier balance equation introduces carrier flux of momentum, momentum balance equation introduces momentum flux or kinetic energy, and kinetic energy balance equation introduces energy flux. The way out is the following. Often the infinite series of balance equations is truncated after 3 balance equations of carrier, momentum, and kinetic energy using a phenomenological closure relation for the energy flux Fw. So what you do is you pause or you stop after the 3 equations. Now you do not have a relation for Fw solved from other fundamental equations. So what do? You make an assumption about Fw. This assumption is based on your observation of how kinetic energy flux varies with various quantities. For example, consider the heat flux. You can write the heat flux as proportional to the temperature gradient. So you write heat flux is equal to a constant into the temperature gradient. Now how do you write this? It is not as though you have derived this relation from fundamental principles, but you observe an Ohm's law kind of relation or linear behavior between cause and effect. So for a spring, for example, you write the force is equal to a constant into the displacement. So the force exerted by the spring is proportional to the amount by which you elongate it. Now using these kind of observations, you are writing an approximate relation for Fw. So this approach of writing a relation based on some intuitive understanding but not necessarily from fundamentals is called a phenomenological approach. So you are using a phenomenological relation for Fw to terminate the series of balance equations. and that is why the relation that you use for Fw is called a closure relation, because now the form is getting closed, the form of equations is getting closed, it is not going on and on. It turns out that the carrier momentum and energy balance equations are sufficient to model device phenomena including non-equilibrium effects of both steady state and transient variety, such as the velocity saturation, velocity overshoot, etc. These effects we have already introduced in the context of the qualitative model of the various transport phenomena. Let me just alert you to some of the synonyms. Many times some words are used interchangeably to mean the same thing. For instance, the terms non-equilibrium, off equilibrium, hot carrier are often used to mean the same. Similarly, the word transient means the same as non-stationary, and the word non-local effects and velocity overshoot effects are also used interchangeably. So let us summarize our picture of the equations and boundary conditions. So at this point of time our picture looks as shown in this slide. Let us focus on the transport equations, because we already are familiar with the Maxwell's equation under quasi-static approximation and neglect of the magnetic flux B. So you have the carrier balance equation, that is dou n by dou t equal to 1 by q into dou by dou x of Jn plus the generation rate of electrons and recombination rate of electron hole pairs. Often we write the recombination rate in this form of carrier concentration minus the equilibrium value divided by the minority carrier lifetime. The momentum balance equation on the other hand is given by dou Jn by dou t equal to 2q divided by the effective mass of electrons, the whole term multiplying the spatial derivative dou by dou x of Wn, the energy density, plus q square into electric field into the carrier concentration n divided by the effective mass Mn, minus the current density Jn divided by the momentum relaxation time. The energy balance equation is given by the time derivative of Wn is equal to dou by dou x of the energy flux Fw plus the heat generated, the ohmic losses, so called ohmic losses, electric field into the current density at that point, minus Wn minus the equilibrium value of Wn, that is Wn0, divided by the energy relaxation time plus a source term which signifies the contribution of electron hole pair generation recombination processes to the carrier energy. Now you have 3 more equations for holes. So we have written down these equations for electrons, you have 3 more equations for holes, so you have 6 equations here, plus one must not forget the equation for heat flux, and that is given by the mass density rho into the heat capacity C multiplied by the time derivative of the lattice heat lattice temperature equal to the spatial derivative or divergence of the thermal conductivity times the gradient of the temperature, lattice temperature, plus the electric field into J, the ohmic losses. So this term is analogous here to this term here, E times Jn, except that the J here includes the electron current density as well as the hole current density, plus the heat that is generated by excess recombination processes of electron hole pairs. So R minus G into the energy gap. So the Maxwell's equations give you the information about the electric field, and they in turn require the input as concentration of electrons and holes, because you need to use the space charge here to get the electric field. Now these are supplied by the transport equations, which also give you the current density Jn and the whole current density Jp, and these transport equations require the electric field information as the input, which is obtained from the Maxwell's equations. You impose suitable boundary conditions to solve the differential equations. So that is our picture, and this is the transport model that will be used to analyze various devices. So in fact these are the equations which are used very often. We will also see some further approximations of these equations to derive what is called the drift diffusion transport model, which is much more common than the model based on all the balance equations. Now let us look at implications of some physical conditions on transport equations. So very often we do not have to deal with all the terms of these differential equations, they look fairly formidable. However, I want to remind you that we have said that all these equations have a common form, because these are all talking about conservation, balance or continuity of some physical quantity, and they can be related to the familiar whole continuity equation. So this you must always bear in mind. Let us start with the physical condition of equilibrium. So under equilibrium, current density Jn, the kinetic energy flux Fw, both are 0, because the condition of equilibrium is no net flow of charge or energy. Okay, so that is what is captured here when you say Jn and Fw are 0. Further, another condition of equilibrium is that the temperature is uniform throughout the device. Now this is expressed in the form the gradient of TL, lattice temperature, is 0. Further, you do not have any generation or recombination processes, excess generation or recombination process, right. G and R represent excess generation and recombination, so these are 0. Similarly, the kinetic energy density of electrons Wn is equal to the equilibrium value. Now as a consequence of this, many of the terms in these equations will drop out. So the equilibrium picture of these equations is as follows. So you see most of the terms are getting dropped out, the carrier balance equations really becomes trivial. So things are not changing with time under equilibrium, therefore all the time derivatives are 0 here in this column, the left hand side of all equations are 0. Further, since Jn itself is 0, this term does not exist, G and R also are 0. So carrier balance equations really becomes trivial, all terms equal to 0. Similarly, you find energy balance equation also, all terms are becoming 0, and same thing about the heat flux. However, it is interesting to note for the momentum balance equations there are two terms which are non-zero here, okay, while Jn by tau m goes to 0 because Jn is 0, and the left hand side is also 0 because time derivatives are absent. Now what does this mean? Now you see that there can be conditions of non-uniform doping in a semiconductor, though the semiconductor is under equilibrium, and you would recall from discussions in the first level course that under non-uniformly doped conditions you do have an electric field to counterbalance the diffusion that is created by non-uniform doping. So non-uniform doping causes the majority carrier concentration to be non-uniform and the minority carrier concentration also to be non-uniform, and therefore there are diffusion currents of mobile carriers, electrons or holes. However, since under equilibrium there should be no Jn or Jp, the diffusion current should be balanced by drift currents, and that is how an electric field is set up. Now that is the kind of situation that is described by these two terms. So you see for a non-uniformly doped semiconductor E is non-zero. However, since other terms are 0, these two terms should sum to 0. So therefore it shows that there is a non-zero spatial gradient of kinetic energy density. Now as we will see, this is due to the presence of the carrier concentration gradient, okay, and that is causing a diffusion current. Let us take the next important condition, namely the steady state. In this case all time derivatives go to 0, time derivative of all quantities, dou by dou t of any quantity is 0. So what is happening is the left hand side of all these equations is being set to 0. Let us take another important situation, spatially uniform conditions. In this case the spatial derivative of quantities go to 0. For example, in carrier balance equation dou Jn by dou x is 0, in momentum balance equation dou Wn by dou x is 0, in energy balance equation the dou by dou x of Fw is 0. In fact, this is the reason why in many situations you do not really need information about Fw, because they are spatially uniform. And finally, in the heat flux also the gradient of the lattice temperature is 0. Now let us go on to model the velocity field curve based on this information about balance equations. Now this curve is shown here for silicon at 300 K, for electrons and holes. So basically what we want to model is a linear increase for small electric field followed by a saturating tendency for large electric fields. As we have remarked, whenever we want to develop a model for any characteristics, we must also have a diagram of the biasing arrangement of the device in mind, which tells us what is the device geometry and what is the applied signal. So this is the situation that is depicted here. So you have a uniform semiconductor, a voltage is applied, DC voltage is applied and there is a current, and this DC voltage is very slowly varied. This is very important, that we are not varying it rapidly. So the variation is so slow that corresponding to any voltage the conditions in the device can be regarded as steady state. This voltage sets up an electric field E that is causing the electrons to move from the right contact to left contact, but holes move from left to right. So first we should write down the conditions before writing the equations. So the conditions are steady state, then spatially uniform and no impact ionization. Now why are we saying this no impact ionization? Because we are dealing with high electric fields here when the velocity tends to saturate, and we want to be sure that our fields are not so high that there is excess generation because of impact ionization. Okay? So we will not analyze that situation where impact ionization may be present. Now what would our equations look like? So let us put down the equations here. We are doing this modeling for electrons, and now let us simplify the equations using the conditions. So which are the terms which drop out? So since situation is steady state, all the left hand side terms here have dropped out. Since it is spatially uniform, the spatial derivatives have dropped out. This is shown by the red crosses here, because spatially uniform is shown in red color, the steady state is shown in black color. And then no impact ionization, this means there is no generation, excess generation of carriers. Now evidently this means that the recombination also is 0, because excess recombination is 0, because you see this term is 0 in carrier balance equation, this term is 0, this term is 0, so evidently R has to be 0. This means the electron concentration would be equal to the equilibrium value of the concentration. Now look at the term SE in energy balance equation. Now we are neglecting a contribution of generation recombination processes to the kinetic energy. Now this is because we have just now remarked that there are no excess generation or recombination, right? So therefore there is no energy contribution from these processes. Also note that because the G and R have become 0 as obtained from the carrier balance equation, the R minus G term here in the heat flux equation drops out. Now you see there is a problem, we have to introduce a sink term here, otherwise the heat flux equation becomes inconsistent. Why? Suppose we do not have the sink term. Now you see what is happening, because of steady state condition this term is 0, time derivative is 0, because of uniform conditions, that is what we have claimed, the spatial derivative is 0, and because there is no excess generation or recombination, this term is 0. Now this seems to lead to the condition that E dot J is 0, that is no heat generation or ohmic loss, now which is evidently wrong because E is non-zero and J is non-zero. So therefore there has to be another term, non-zero term here. Now what has happened is, we have not taken into account in this equation the rate at which heat is lost by the semiconductor to the surroundings. The equation that we have written down here talks about the sources of heat within, or sources or sinks of heat within the semiconductor. So that is not sufficient, we need to have a sink term here, otherwise there will be inconsistency. So that is the sink term. However, in practice we are not going to use this heat flux equation, so we will not concern ourselves with the sink term here. So we will work with the carrier balance, the momentum balance and energy balance equation. So the simplified forms of these equations are given here after all the other terms have been removed. So carrier balance equations gives the electron concentration equal to equilibrium value, the momentum balance equation gives equality between these two terms, and energy balance equation gives you this. Now what about tau m and tau e? The relation for tau m and tau e have to be obtained from quantum mechanics, because they are related to the scattering phenomena, and we have discussed that the scattering itself has to be treated quantum mechanically. So these relations are obtained from quantum mechanics, we have not done this derivation, we are accepting the result. Now that being the case, we need to express the energy balance equation in terms of the carrier temperature, because you see the equations derived for tau m and tau e from quantum mechanics consist of the electron temperature here. To convert the energy balance equation into equation for electron temperature, we use this relation for kinetic energy density Wn in terms of the carrier temperature Tn. So recall that this kinetic energy density can be split into two parts, a random component called the thermal component and a directed component called the drift component. Since it is energy density, you have the electron concentration term coming there. Now usually we make the approximation that we neglect the directed component, we assume that the random component is very large. Now this approximation is definitely quite good for very high electric fields where the directed component saturates. It is also good for very low electric fields, okay, when the directed component is small. You know that even under equilibrium you have a large kinetic energy density because carriers are moving about randomly. So near equilibrium also the directed component is very small compared to the random component, and for very high electric fields when the velocity saturates, the random component goes on increasing. So even there this approximation holds good. Somewhere in between the approximation may not be valid to that extent. However, we shall continue to use this approximation over the entire range to get a simple equation. Now I leave it as an assignment to you to show that simple algebraic manipulations with these equations here, in fact you do not have to use the carrier balance equation, this is independent, you basically have to work with these two equations because the Jn here enters in both these equations. Really these are two equations to be solved simultaneously, and in this you substitute Wn in terms of Tn from here and also use this formula for tau m and tau e. The result turns out to be in the following form: the drift velocity is a function of electric field given by minus mu n 0 into electric field by square root of 1 plus electric field by a critical electric field square, in which the mu n 0 is q times the momentum relaxation time under equilibrium by the effective mass of electrons, and the saturation velocity is obtained by taking the limit E tending to infinity in this equation. And what you find is that when you take E tending to infinity, you can see that this term will be very large, and so square root of a square term is E itself, and therefore this E will cancel with this E, and therefore you will get a saturation value. That saturation value should be shown as thermal velocity into square root of tau m0 by 6 times tau is 0. Okay. So this tells you that the saturation velocity is of the order of thermal velocity. Now you will have to use the relation for thermal velocity. So you know that the kinetic energy density or kinetic energy per carrier under equilibrium, you have the relation half m into V thermal square equal to 3 by 2 times the Boltzmann constant into the lattice temperature. So you will have to use that relation. Let me give you some hints for this assignment. So using the previous slide, show that the momentum balance equation leads to this formula for Vd. Then if you combine the momentum balance and energy balance equations, you will obtain this. So the algebraic manipulation is your responsibility. I am telling you some hints for the individual steps. Now where E critical is a function of the lattice temperature TL, Boltzmann constant K, the electron charge Q, effective mass of electrons Mn, the energy relaxation time close to equilibrium, and momentum relaxation time close to equilibrium. And then you can combine these two equations to show this model. I would also like you to estimate the order of the critical electric field, the mobility of electrons, right, for low electric fields mu and 0, saturation velocity in silicon using approximate values of these quantities. Now just to give you some feel, tau m0 is of the order of a few tenths of a picosecond, and tau e0 is of the order of picoseconds. Okay. You can get the other quantities from books or internet. Now here is the graphical representation of the results. This slide has actually been pulled up from the qualitative analysis, right, qualitative modeling. So why does the velocity saturate? Now this is your velocity field curve. Now why does the velocity saturate? It is because the momentum relaxation time is falling down, okay, and at this end it is inversely proportional to electric field. Now why does the momentum relaxation time fall down? It is because of the electron temperature rising rapidly here, okay. So this is the graph representing the result of energy balance, which is Tn by TL equal to 1 plus E by E critical square. The result of carrier balance is N remains equal to N naught. Now this shape of tau m as a function of electric field is obtained from quantum mechanical relation tau m equal to tau m0 into square root of TL by Tn, where the Tn is expressed in terms of electric field from our energy balance equation. So the momentum balance equation on the other hand gives you this expression for the drift velocity. Note that under quasi equilibrium conditions very close to the origin here, you have a straight line segment which can be cast in the form of minus of mu n0 into E. So here is a summary of our model. The conditions in our semiconductor are steady state, spatially uniform, and no impact ionization. Under such conditions, if you vary the voltage across a semiconductor slowly, your current you increase the voltage slowly, the current versus voltage relation will be linear in the beginning and then it will approach saturation. So since mu n0 is the constant, slope in this linear segment close to the origin or for low fields, this is called low field mobility. Now similarly, let us look at the velocity overshoot, modeling of the velocity overshoot, which is a little bit more complex issue as compared to the velocity saturation. However, we will find that the same set of energy balance equations will be used here, and we will be approximating the terms depending on the condition. So our conditions are that you have a semiconductor uniform and you are suddenly stepping the voltage to a high value. As a result, there is a transient current, and this transient current, which is reflected in the drift velocity, varies as shown here. So it goes up and it overshoots the saturation value. This is the electric field step because of the applied voltage. Now we will assume that the conditions are spatially uniform and there is no impact ionization. Again, because this is a high field effect, we are not going to ignore impact ionization, so that our analysis is simple. So let us begin with the equations again. Now because of spatial uniformity, the spatial derivatives have all been neglected. Now look at this carrier balance equation. This term is 0 because no impact ionization, the term G is 0. Now we can show that the consequence of this relation dou n by dou t equal to minus r is that the r should also be 0. Now why? Now this is because you see, when at the instant when the electric field is just stepped, so you take the condition, initial condition, at this point there is no excess generation, so there is no excess recombination either, so your n is equal to n naught. Now under steady state conditions, when dou n by dou t is 0, r has to be 0 because other terms are 0. So again under steady state conditions also your n is equal to n naught. So initial condition at t equal to 0 when the electric field is stepped, n is equal to n naught, finally also n is equal to n naught, and if you now substitute this form of the recombination process here, you find that dou n by dou t versus n should give you an exponential relation. Now an exponential relation whose initial value is n naught and final value is n naught, so you know that this segment is nothing but a constant segment. Now that is why the carrier balance equation gives you n is equal to n naught. Now again we have removed the contribution of the generation recombination processes to the energy balance equation SE, because there is no generation or recombination over and above the equilibrium value. The simplified equations are put here. We are following exactly the same approach that we followed for velocity saturation, okay, velocity field curve. The only thing is the equations are a little bit more complex because here time derivatives have to be considered. So tau m and tau e are obtained from quantum mechanics, and since they are given in terms of the electron temperature, we convert the kinetic energy balance equation to an equation in terms of electron temperature, for which we use this expression and we neglect the directed component, regarding the thermal component to dominate. Now the result of that would be equations shown here. Okay. Now what we have done is we have also removed the term Jn, and instead we have converted the equation into an equation of the drift velocity. This is done readily because you know that Jn is nothing but minus q times the electron concentration into the drift velocity. So if you divide the Jn equation by minus q times n, you get the drift velocity, because ultimately we want to model the drift velocity and not the Jn, we want the velocity overshoot characteristics. So now you find that the momentum balance and energy balance equations are coupled through drift velocity and the electron temperature. So you find the drift velocity entering here, and you have the electron temperature entering in momentum balance equation. Why? Because the tau m depends on electron temperature as shown by this formula. So the first step will be to simplify or decouple these equations. Okay, so these are approximations that we are doing for analytical solution. Otherwise numerically you can always solve two coupled differential equations, but we want analytical solution. So how do you decouple? So you decouple momentum balance and energy balance equations assuming tau m is constant in the momentum balance equation. So here we will assume tau m to be constant, and Vd is approximately equal to Vsat in the energy balance equation. So moment you set Vd as a constant equal to Vsat, you do not need this equation for this velocity, and moment you set tau m as constant, you do not need the equation of the electron temperature, right, to estimate this value. So the results are shown here. So we have replaced Vd by Vsat, a constant, and we have removed the tau m because it is a constant, but we still have tau e as a function of electron temperature with a square root sign here. Now that is going to complicate the solution of this differential equation. So if you put tau e as a function of square root tau n, so what we will do is, next simplification we do is that we simplify energy balance equation assuming tau e is constant. So here we will set this to be constant, so we remove the tau e expression also. Now we are dealing with considerably simplified equations. You can see that this is a simple differential equation, first order, and its solution will be an exponential for Vd as a function of time. Similarly, this is an equation which is also a first order equation in tau n, in Tn, that is electron temperature, and it will also give you an exponential solution as a function of time. Now that is what is shown here. So the momentum balance equation gives you an exponential relation for the drift velocity as a function of time, assuming that tau m is constant, and the energy balance equation gives you equation for electron temperature as a function of time. Now these two solutions have been plotted here. So Tn is exponentially rising from TL under equilibrium to some saturation value under steady state, okay, corresponding to the high electric field or high voltage that you applied. So this is the electric field step, and similarly the momentum balance equation gives you an exponentially rising drift velocity as a function of time. Now here we have shown approximately to scale the fact that the momentum relaxation time tau m is less than the energy relaxation time tau e. So this variation in Tn happens over a much longer period than the variation in Vd, okay. You will recall from the qualitative modeling that we had said that the fact that tau m happens to be less than tau e or much less than tau e is actually very important for the velocity overshoot to occur. Okay, now we do not seem to have got the velocity overshoot yet. Now that is just one step ahead now. So what we do is we now set the tau m as a function of the electron temperature Tn. So we are solving for electron temperature from this equation, and that value we will substitute here to get the tau m, and we will make the tau m as a function of time. Now notice that this is an approximate approach. First we assume tau m to be constant to get exponential solutions, but now we are introducing the time dependent tau m, okay, to get the velocity overshoot. So note that the tau m is a temperature dependent quantity in two places of the momentum balance solution of the momentum balance equation here, this place as well as this place. Unless you assume the tau m to be time dependent in both places, you will not get the overshoot. And how does it give you the overshoot? That is represented here. So your tau m varies, it decreases from high value to a low value. Two values are tau m 0 and tau m infinity. So the exponential solutions for two extremes assuming constant tau m are given here. This tau m 0 and this tau m infinity. So evidently when you put the tau m to be time varying between these two limits in this equation, your curve is going to follow the curve for tau m 0 up to a point, and then it will drop and then come to tau m infinity. So in fact this is what I leave it to you as an assignment to show, that when you assume tau m as a function of time here according to this formula, you will actually get a velocity overshoot. Okay, so you will have a region where the velocity versus time will have a negative value, or you can also analytically approach the problem as finding out the derivative dvd by dt and show that it goes to 0 at some non-zero time, and where it goes to 0 the d square vd by dt square has appropriate sign to show that it is a maximum. So this is our model of velocity overshoot of these characteristics. Now you can improve the model, you can also include the variation of energy relaxation time with time, okay, because energy relaxation time also will change, in fact it increases because the electron temperature is increasing with time. So I can feed this time dependence at this location and this location, and then I can solve these equations. My computation will be more, but a model will be more accurate. So this is the assignment: establish that the following equations indeed show velocity overshoot when tau m is much less than tau e. First, using simple analytical reasoning. So I told you you can take derivatives and find out the sign of the derivatives and so on, and then by calculation and plotting. So you can actually calculate and plot, you can use MATLAB or any other calculator. Now finally let us discuss the model for current density. You will recall that when we discussed the various transport phenomena, semi-classical transport phenomena, we said that current can be because of drift, diffusion or thermoelectric current, so temperature gradient. So we want expressions for the current density for these driving forces. Now this is what we would like to get from the balance equations. The relevant balance equation here is the momentum balance equation, because it is this equation which contains the Jn term. Let us show how some approximations of this equation will lead us to a simple model for current density Jn in terms of the various driving forces, namely the electric field, the concentration gradient and the temperature gradient. So we have reproduced the momentum balance equation, and note that this quantity here is called the mobility, which is a function of electric field because tau m varies with electric field. The first approximation we make in this equation is the quasi-static approximation. We assume that the time varying term here is small. Now this approximation works fairly well because momentum relaxation times are very small, and the quasi-static approximation amounts to assuming that dou Jn by dou t is much less than Jn by tau m. So you see, we have said that whenever we neglect a term, we always do so with respect to or with reference to another term. So it is not as though some term becomes 0 and that is why we neglect it. So whether a term is small or large depends on its relative value compared to other terms in the equation. So the simplest term that you can compare with to get a feel for what this approximation means is Jn. So when we say tau m dou Jn by dou t is much less than Jn, then it means the current changes in a duration much greater than tau m. So long as your changes in current density are in a time that is much more than fractions of picoseconds, right, this will work. So this is going to fairly high frequencies. The next approximation we make is that thermal energy is much greater than the drift energy. So this approximation is related to Wn. You see, we have to find out this spatial derivative of Wn. So we are doing the approximation for that purpose. Now writing the equation in terms of electron temperature, this amounts to the approximation Wn thermal much greater than Wn drift amounts to assuming that this half NKTN plus half Nm men Vd square is approximately equal to the thermal component itself. So, we have neglected the directed component, and we are using half here because we are using one dimensional version of the equation. Now, if you use 3 dimensional version, you know that this would be 3 by 2 NKTN. Now, when you differentiate this term with respect to x to get dou x by dou Wn, so you will get two terms here, one related to the derivative of n with respect to x and other related to derivative of Tn with respect to x, because you have the product of n and Tn. Now, let us substitute the result of differentiating Wn with respect to x into the current density equation and see how it looks like, or rather the momentum balance equation, and see how the equation looks like. So, now under these two approximations, namely the quasi-static approximation where we have dropped out the dou Jn by dou T term and using this derivative of the current density with respect to x, the equation becomes Jn is approximately equal to q times the diffusion coefficient of electrons multiplied by the concentration gradient plus q into carrier concentration n into d suffix T n. This is called thermal diffusivity in analog to the diffusivity associated with the concentration gradient. So, q into carrier concentration into thermal diffusivity into the temperature gradient. So, here we are looking at the carrier temperature plus q times the carrier concentration n into the mobility mu n into E. Now, the diffusivity dn, thermal diffusivity d suffix Tn and mobility mu suffix n are all functions of electric field. So, this term represents diffusion, this is related to carrier concentration gradient. The term dependent on the temperature gradient represents the thermoelectric current, and the term dependent on electric field represents the drift current. Let us look at the formulae which relate the diffusion coefficient and thermal diffusivity to the mobility. So, this is the so called Einstein relation you have come across already in the first level course. What we see here, however, is that the Einstein relation you had discussed in the first level course was related to the equilibrium condition, whereas here we are using it for high electric field high electric field regions also. So, that is the difference. Similarly, the thermal diffusivity d suffix Tn depends on the mobility via this formula k, that is the Boltzmann constant, by q into the mobility. Now, this is the reason why one talks only of the mobility of carriers in a semiconductor, right, and one tries to model mobility, measure mobility and so on. So, you will find in books the data for mobility given, right, but many times the data for diffusion coefficient or thermal diffusivity is rarely given. The reason is you can always derive this data from the mobility data because of these relations. So, these relations are therefore very, very important. Now, the two approximations have been put in abbreviated form here because we are going to encounter more approximations, okay, as we consider formulae for mobility. So, the mobility mu n is a function of E and the function is given by this formula. This we have just derived when we discussed the velocity field relation. We modeled the velocity field relation from the balance equations. Therefore, you will recall from that modeling exercise that there are some approximations associated with this result also. Now, those are the quasi-static approximation of the energy balance equation, in which we neglect the dou Wn by dou T term. Now when you neglect this term, evidently this term is small. However, we have been emphasizing that a term is small not in that it is absolutely 0, but it is small compared to the other terms. So which term do you compare with? So as we have seen here, as we have shown here, you compare it with the term Wn minus Wn0 by tau e. The reason for that is, look at the energy balance equation. Now here, before I proceed further, I wish to point out an error in this equation the way it is written. There should be a negative sign here, and this negative sign had actually been missed in the tables that I shown earlier in this lecture. So please make that correction, okay, if you have taken down notes, and note this correction. However, this does not affect any of our results that we have discussed, because we have already shown that we do not use this term at all in modeling, at least the kind of modeling that we have done. Now returning to this energy balance equation, we want to neglect this term, so we would like to compare this term with any of the terms here. So one term that you can compare it with is this. So just like for momentum balance equation, we moved this Jn term from the right hand side to the left hand side, and that allowed us to compare these two terms. We can move this term to the left hand side, right, and then it will appear as plus Wn minus Wn0 by tau e. So we remove it from here. Now we can compare these two, right, and if this is very small compared to this, then you say that the quasi-static approximation or steady state approximation for kinetic energy is applicable. So that is what we have done here. Similarly, we made another approximation, namely that we assumed the conditions to be uniform when we derived this formula for mobility. So you will recall that this formula for mobility involved a relation for the electron temperature in terms of the electric field, and that is where we have done the approximation that we were talking about when we derived that equation for electron temperature. So spatial non-uniformity of Wn in the momentum balance and Fw, that is the flux of kinetic energy, in the energy balance equations are small. So for example, dou Wn by dou x is much less than q n e divided by 2. So here again we are comparing the term that we are neglecting with other terms in the equation. Look at this. So dou Wn by dou x in the momentum balance equations comes here, okay. Now we compare it with this term. You can see that mobility can be removed, and so if this term is much less than this term, then you can neglect this term, right. That is what we are saying. One can similarly write down an expression for neglecting Fw. So if you want to do that, you should look at the terms here. You can compare it, for example, with this term for neglecting, right, and you can write down a similar relation. Here is an assignment before we close the lecture. Express the thermoelectric current density in terms of the Soret coefficient Sn equal to k by q into carrier concentration n into mobility equal to carrier concentration into the thermal diffusivity. So dTn is called the thermal diffusivity. Determine Sn and dTn for an n-type silicon of 1 in 10 power 17 per centimeter cube doping, and estimate the thermoelectric current in this sample for a temperature gradient of 1 degree centigrade per micron. Now since we are at the end of the lecture, let us make a summary of the important points. So in this lecture we developed the energy balance equations approach for modeling devices. We showed that the Boltzmann transport equation is equivalent to an infinite series of balance equations. Now this series is terminated after 3 balance equations, namely those of the carrier concentration, the momentum density and energy density. and this termination is achieved by a closure relation for the energy flux that enters into the energy balance equation. Then we showed how using these three balance equations you can model velocity overshoot, velocity saturation, and the current density involving the drift current, the diffusion current, and thermoelectric current. And we showed that you need to do a number of approximations of the momentum balance equation to achieve this simple relation for current density, in which the current density is shown as sum of three components, one due to concentration gradient, one due to temperature gradient, carrier temperature gradient, and the other due to electric field. We will continue the discussion in the next lecture.